sections 3.1 and 3.2. So we started 3.1 last time. We're going to finish it today and maybe get into some 3.2. So you have two homework assignments, which, well, I was going to make them due Thursday, but then I realized that Thursday is on fall break. So I decided to make them due Wednesday. So they're due tomorrow night. But I put in the email that I sent out. Did everyone receive my email? Okay, I put in the email that if you need an extend your next assessment, oh, this is going to be the death of me. How do I get this thing out of low power mode, do you think?
Tell Siri to turn off low power mode.
Okay, look, I'm not an Apple user. This is. Yeah, you're right. But I'm an Android phone user. You can help me out.
You need to put it in your little accessibility thing.
Yeah.
Oh yeah, that's what's
Let me
up.
help you out real quick, actually.
Yeah, do it for him.
Thank you.
Where is it at? Isn't it?
You just turned it
All the way
off.
at the bottom.
It was in battery, right?
No.
What's it called? Preferences?
No, it was just right there when you were in battery.
Shortcuts.
Okay, I got you.
What? There
Oh,
you
you're
go.
adding the shortcut. I see. Smart.
I think.
Where's low power mode?
It's not on here.
Oh, I got you. I will do this. Where's accessibility? Oh, okay, duh.
There it is.
Is there not an edit button?
Let's see.
Oh, duh. Yeah, that's where I just was. Yeah, I don't know.
Oh well.
I'm not that smart.
Well, we got it off. That's what matters. Thanks, Connor.
It might be a control center.
Yeah. I'll figure it out after class when I have unlimited time. Okay, so where was I again? I think I was just saying about the homework. I'll grant an extension if you want it, but they're due Wednesday. For the exam, it's going to be the Wednesday after fall break. So when we come back from fall break, we'll have Monday class where we learn something new that probably won't be on the exam. And then on Tuesday, we'll do a review. So today's the last class that will be basically covered on the exam. So probably it'll be up to 3.2, maybe, if we finish 3.2. We'll see. So that's the exam. My office hours are going to be today from 2:30 to 4. Can I have a show of hands on who's planning on coming to office hours? Okay, we got a few people. So we're going to start in my office and see how many actually show up. Basically, we're just going to work on homework problems. So if you want to finish your homework before break and get some extra help, then just come to office hours today and we'll work on a bunch of homework problems together. If you can't come to office hours, though, the tutoring center is going to be open today and tomorrow from 10 a.m. to 4. Okay, so that's all I have to say about that. Oh, one more thing. I posted an extra credit assignment to Blackboard. So let me show you that on the Blackboard.
I think that's the exponent one thing part that we did.
It was like +2 quiz points.
Yeah, so the extra credit is going to be worth 2 quiz points. I may post another extra credit assignment later. We'll see. But basically, I'll add 2 points to your quiz score, like one of your quizzes, basically. So what you need to do is use the rational root test and long division to fully solve the equation x to the 6th, da 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 da. Okay, so when I do a caret and then a 6 here, it's really hard to see, that's small. But when I do a caret and a 6 here, why don't I just zoom in? When I do a caret and a 6 like that, I mean to the 6th power, okay? So this is 43x to the 4th plus 64x cubed and so on, right? So if you can fully factor this and solve this equation using the rational root test and long division, you're going to need to do long division like many times. But if you do it and you write it out and you show all of your work and you upload a picture of your work to this submission, okay, so you just click on it and you can upload here, then you'll get 2 extra credit points for your quiz. Any quiz, yeah. I'll just find whatever quiz is your lowest quiz and I'll add 2 to it.
Like 2 points or like 2 points where it goes like to 20 points.
What?
Well, all the quizzes are worth 10 points. So what I mean is I will boost one of your quiz scores by 20%. Does
Okay.
that make sense?
Wait,
So
I can't remember. We don't have the option to drop our lowest quiz at the end of the semester.
you do. Your two of your lowest quizzes will be dropped.
So then what if like I did the extra credit and I wanted you to put it on my third lowest quiz?
Okay, yeah, no, I'm not going to. Yeah, I'm not going to give you the extra credit and then drop that quiz. No, I will assign the extra credit at the end of the semester in such a way that it will help you. I promise.
If it's on my lowest quiz, I would still drop.
Okay, Morgan.
Like, what if we try and get it wrong? Will we still get any credit?
No.
Okay,
No, that's a good question. If you try it and get it wrong, then I will tell you that it is wrong, and you can try again. Yeah, you can try unlimited times.
Oh, we have till December. Oh, so
Yeah, you can do it whenever you want.
that was like, oh.
Yeah, so it's open even if you decide later that you want extra credit. Okay, any other questions? Any questions on anything else administrative before we start in on content for today? I feel like there was something else, but maybe not. Oh well. Let me remind you what we talked about last time. So we were discussing exponential functions, which the thing about exponential functions is that they have an exponent which is the independent variable. Okay, so the independent variable is in the exponent. Okay, so we have an x in the exponent. So that's the difference between x squared and 2 to the x. Okay, so one of them is exponential, one of them is not. Okay, so that's an exponential function. We reviewed exponent rules. I'm not going to cover those again. 2 points that are always on the graph of an exponential are 0, 1, and 1a, unless you modify it, right, by +3 multiplied by 2, something like that. That's obviously going to shift those points, okay? So if we have a reflection, we reflect. If we have a shift up, down, left, right, squeeze, or stretch, right, then we're going to modify those 2 points. Okay, we talked about exponential growth versus exponential decay, okay? So that depends on whether your a value is bigger or smaller than 1. The domain and range of an exponential function, we also covered. And then we did a class activity on trying to graph these guys where we transform different exponential functions. Okay, so we transform different exponential functions. So this one had like a reflection about the y-axis and a vertical shift. This one had a horizontal shift to the right 1 and a vertical shift down 3. This one had a vertical reflection about the x-axis, a vertical stretch by a factor of 3, right? Okay, then we talked about this last problem, which I had to kind of rush to get through, but I want to go over that one in more detail. So I showed you one way to do it last time, which is the following. Well, we know 2 points that are on the graph of the function, and the thing that you have to understand to do a problem like this is what is the when is a point going to be on the graph of a function? A point is on the graph of the function if, when I plug in the x value in for x, then when I do all of this stuff, I get the y value, which is 18, right? So if I plug in -1, I get 18. If I plug in 4, I get 2 over 27, right? That's what it means for a point to be on the graph of a function. And if you do this, you can see that I achieve 2 equations and 2 unknowns, right? Now, you probably learned how to do systems of equations like 2x minus y equals 3, and then x plus y equals 4, something like this, right? How would we do an equation like this? We would use elimination or substitution, right? We would solve for one of the variables and use it to replace in the other equation, right? Something like that. But the thing about this system is this system we have addition, which is a big difference between doing addition and doing multiplication. Okay, so we actually can't just subtract these 2 equations from one another. Why? Because there's no way for me to subtract a multiple of this equation from the other one and eliminate just one of these variables. Right? So what do I have to do instead? I'm not going to subtract these equations from one another, but I'm going to divide the equations by one another. And if I do that, Well, I have one number equals 18. Another number equals this number. If I divide the two numbers on the left, it should be equal to the two numbers on the right, because the numerator on this side is the same as the numerator on this side, and the denominator on this side is the same as the denominator on this side. So these two fractions are the same. If I divide these two equations by one another, we get a new equation. And in that new equation, we cancel c. That was the crucial step, was cancel c. So now what do I have? Now I have 1 over a to the 5th equals 18 times 27 over 2. Okay, so we get 9 times 27, which is 1 over a to the 5th is equal to, let's see, this is going to be 3 squared times 3 cubed. That's probably an easier way to write it, which would be 3 to the 5th. So if I multiply a to the 5th over to both sides, we get 1 equals 3 to the 5th times a to the 5th. And therefore, a to the 5th equals 1 over 3 to the 5th. And take the 5th root on both sides tells us that a should be equal to 1/3. Okay, so now I got a. But I'm not supposed to just find a, am I? I'm also supposed to find c. How can I now find c, now that I know what a is? Yeah, you can plug in, right? I can take a and plug in to one of these equations. I know that c divided by a is equal to 18 by this equation. And I know what a is. A is 1/3, which means that 3c is equal to 18, which means that c is equal to what? 6, right? Sorry, yeah, c divided by 1/3 would be 3c. Okay, so c equals 6. So therefore, q of x is equal to what? 6 times 1/3 to the x. Okay, so that was that example from class, the challenge problem that we had. This is one way to do it, is to set up these two equations and divide them by one another. Okay, divide them by one another. One alternate method, which I want to show you, would be to do the following. So let me add a page. So the alternate method would be to take one of these and solve it for c. So if I multiply both sides by a, if I take this equation and multiply by a on both sides, what would I get? C equals 18a, right? C equals 18a is what I would get. And so what I can do then is plug this in for c here. And then what would I get? I would get 18a times a to the 4 equals 2 over 27. And so therefore, a to the 5th equals 2 over 27 times 1 over 18, which tells us a to the 5th equals 1 over 3 to the 5th, which tells us a equals 1/3. Okay, that's another method. You can just solve one of the equations for one variable and substitute. Use substitution into the other equation. Yes?
How did you get rid of the -1? Like, it's to the negative first power, so like, how did you get rid of that?
Okay, so what I did there was, I probably should have written it all the way out. So let me show you. So I took the equation c times a to the -1 equals 18, and I multiplied by a on both sides. So if I multiply by a on both sides, then on the right side, you see I get 18a, right? And then what do I have on the left side? I have a to the -1 times a to the 1. What do I do with the powers? You add them. If I add 1 to -1, what do I get? I get 0, which means that on the left-hand side I have c times a to the 0. What is a to the 0? 1. That's what I did there. So a to the, but loosely speaking, you can think of a to the -1 means I'm dividing by a. If I'm dividing by a and I multiply by a, those are going to cancel out. Does that make sense?
Yeah.
Okay. So that was how I did that. So that's another method that you can use to solve this, okay? I just want to be explicit that this type of problem is pretty important, I would say, for this class. What does it mean if a problem is important for the class? There's a good chance it'll show up on a test. Okay, there's definitely some of these on your homework 3.1, so practice them. Make sure you know how to do this kind of problem because I like putting these types of problems on tests and quizzes and stuff. Okay, so that's solving for the equation of an exponential function given 2 points. Are there any questions on either of the two methods that we used? Okay, doesn't seem like there are, so that was wrapping up the last class. So now let's move on to something new. And I promised you last time that in this section we were going to learn the most important thing about math that you ever learned in your entire life. And I'm not joking when I say that this could mean the difference between you retiring at 65 versus retiring at 75, okay? That's 10 plus years that you could be spending with your grandchildren or with your hobbies or something like that, right? So we want to understand compound interest, okay? It's the number one most important thing about math ever. Well, ever? I don't know, but probably like for the common person. It's the most important thing. Okay, so what is this formula here? Okay, so this is the compound interest formula, which tells us how much money I am going to have in the future, right? If I can understand how much money I'm going to have in the future, then I can plan for the future. I can have an understanding of what my life is going to look like ahead of me, right? So A of t is going to be the amount of money that I have after t years. So this is a function of t. And all of the other numbers here are constants. So p, r, and n are all just numbers, okay? So when I plug in 35 years, this equation, I will multiply all this stuff out, I'll do the powers, and I will get the amount of money which I'm going to have in 35 years, supposing that I initially invested P dollars, okay? So this is the key here to all of these variables. P stands for principal, which is your initial investment. Principal. I can never remember if it's LE or AL for money. No, for money?
Yeah, it's LE. AL is for like a principal of a school.
Yeah, but principal is also used for principal square root.
I used to do a dollar sign.
Principal is like, I think it might be AL, but I'll check.
Here, I'll look right now.
Yeah, specifically for money, I think it is AL. Anyways, so that's what the P stands for, and the R is your interest rate, okay? So something like 5% means that R is equal to 0.05, okay? If you're earning 5%, that's a great investment. Okay, so that's interest rate, and then N is this number, which is the number of times per year which your interest is compounded. Okay, for example, you can compound your interest monthly or annually or semi-annually. So one thing that is a little bit confusing about this formula is that R is what's called the annual interest rate, the annual interest rate. And the number of times per year which it is compounded might make you think, well, if I'm getting 5% interest, then I get 5% every month. No, it's not like that. It just, yeah.
It's AL because of it,
Yes.
it says it's rank or importance. It's the noun or adjective referring to someone or something which is highest in rank or importance.
Okay, so principal with an AL for financial math. All right, so what was I saying was, okay, if you make 5% compounded monthly, What they mean is 5% annual compounded monthly, which is super confusing. You'll notice that the banks love to confuse you. So what does that mean? What that means is your interest is going to be compounded annually, and you are going to make about 5% interest over the course of 1 year. Okay? So when they talk about an interest rate, okay, typically what they mean is annual effective interest rate, okay? So they're going to try to confuse you with this, but we'll see some examples later of how this is confusing. So what it means is when you see R equals annual interest rate, what they mean is you need to put 0.05 wherever you see an R, okay? And the number of times per year that is compounded, that is going to tell you what N is, okay? So for monthly, we would do something like, so for 5% monthly, we would do A equals P times 1 plus 0.05 over 12 to the 12t. Okay, this is what we would do for 5% monthly. Okay? Oh, so I literally put an example here. So what does it look like? Let's say we have $1,000 at 5% annual compounded semi-annually. How much money am I going to have after 1 year? Well, I take 1,000, multiply by 1 plus 0.05 divided by what? Compounded semi-annually means how many times per year? Twice per year. Semi means half. So half year, compounded every half year. So we get 2 times per year. So to the 2t, but t should be 1, right? So I'm going to put 1 here for t. So if I do this, what do I get? Let's use the calculator. Oh yeah, we're going to use calculators for this. So we've got, what, 1,000 times 1.025 to the 2, right? So I need 1.025 times 1.025, and then I multiply that with 1,000, and I get $1,050.62, 62.5 cents. Okay? So that's how much money I would have after 1 year if I was earning 5% annual interest compounded semi-annually. So it's a little bit confusing because they say 5% compounded semi-annually. Am I getting 5% every 6 months? No, if I was getting 5% every 6 months, I would have more than $1,100, right? But I'm also not earning exactly 5% annual, am I? Because exactly 5% annual would mean I would have $1,050, but I have a little bit extra, right? So it's kind of confusing because if you have 5% annual compounded semi-annually, what it means is that your interest rate is basically going to be close to as if you were earning 5% annually. But actually, we see in this case, it's a little bit better. We earned an extra 62 cents. Yeah, we love extra money, right? Okay. So what my goal is for you all is to become informed citizens who understand compound interest so that the bank can't lie to you. Well, they're not going to lie to you, but they're going to tell you things that sound like they mean something different than what they actually do. And I want you to not be tricked by them. Okay, so one more type of interest we need to talk about is continuous interest, okay? So continuous interest is, well, what would happen if I compounded daily? Or what if I compounded twice daily? Or once every minute? Or once every second, right? Well, the interest rate, the effective interest rate, would be different for each type of compound interest which I use, right? But if we took the limit of the interest rate, if we took, well, what if we allow n to go to infinity? Well, what is this number going to become close to? Well, there was someone very smart back in the day, I don't remember who it was, probably Euler because it's E, who figured out that the limit figured out that the limit as n goes to infinity of 1 plus 1 over n to the power n is this magical number e. Magical number e. So e is a very cool number. It's e after Euler, which is E-U-L-E-R. Okay, Euler's number. So anyways, what is the number? It's one of those weird numbers like pi. It's irrational. It's 2.718 da 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 something else, right? I only ever remember 2.718, honestly, because it's like how you only memorize 3.14 or something like that. So that's for continuous interest. So what do? We just replace the number that would be, we replace the number here, okay, that would be 1 plus r over n to the n. We replace that by e to the r. We replace that by e to the r. So we have p times e to the rt. So the interest rate is going to go in the exponent now, okay? And now you're going to notice that we don't have a number of times compounded per year, right? Why not? Because we're compounding continuously. That means every millisecond of every day. Actually, more than every millisecond of every day. Okay? So t is still going to be the number of years. R is going to be the interest rate. Now, the difference in the word problems is that they're going to say you are earning 5% compounded continuously. What they mean is you're going to use this formula and you're going to put r up in the exponent. Okay? That's what they mean when they say compounded continuously. Okay? And p is still your initial investment, your principal. And a is the amount of money that you have after t years. Okay, so for example, 5% compounded continuously, $1,000 in 1 year, why don't we do 2 years, will be what? Well, what do? We just plug into the formula. We know a of 2 is going to be what I get when I do 1,000 times e to the... Now, where's the interest rate? The interest rate is 5%. How is that going to enter into my exponent? Am I going to put 5t? Should I do 5t? The interest rate's 5, right? We should do 0.05. Why? Because the interest rate is not 5. The interest rate is 5%. What does percent mean? Cent means 100. 5 over 100. Percent. 5% means 5 over 100. Right? Percent. Right? Okay, so that's... sorry. I just really reiterated that. Okay, so we get 0.05 if we do that division. So I'm not going to do 5t. I'm going to do 0.05 times t, which in this case t is 2, right? So I'm going to do 0.05 times 2. So what do I get? I get 1,000 times e to the 0.1. Okay, so how do I do that? Well, I got to go sideways mode on the calculator. And if you go sideways mode on your calculator, or if you have an actual calculator, then you'll notice there's a button for e. And we just take e, and then we use the to the power button and go 0.1. I wonder if I have a calculator on the iPad. Do I have a calculator? Oh, God.
No, go back to where you were.
Mm-hmm.
No,
I see, yeah, here. Okay, okay. Calculator. I don't have a calculator. Okay. Nah, that's okay.
That's probably have a calculator on it.
Desmos, let's see. Suppose I should have figured this out before class, shouldn't I? Okay, well, anyways, here's what I would do. What I'm going to do is basically type in on my calculator, okay, I'm going to do E and then the caret and then 0.01, something like this, okay, is what I will do. Not 0.01, 0.1 is what I will type in on the calculator, okay, and if you do that, then you get 1,000 times 1.1057 ... Okay, something like this. So if I do that and I multiply it by 1,000, right, then I will get my new money. After 2 years, I'm going to have $1,105.70 something cents. Okay? 71 cents. 71 cents is what I will have left. Okay, so this is basically compounded continuously. So you can see compounding continuously at a rate of 5%. We are actually going to do a little bit better than if we compound annually at 5%, or if we compound monthly at 5%, or so on and so forth. So one other word that sometimes gets tossed around with this monthly interest is they will say you will earn a 5% nominal interest rate. What they mean by nominal interest rate is they mean in name only. Okay, so nominal meaning coming from the Latin root for nom, meaning name. This is how they will describe an interest rate that is basically not really what you think it is. Okay. So this is how we do continuous interest rate. Are there any questions on these two formulas for doing regular compound interest versus continuous interest? Okay, then we're going to launch into a class activity. Okay, so what I want you to do is the following. We have 3 different banks. We have Bank 1. Bank 1 offers you 12% annual interest compounded annually. Bank 2 offers you an account with 12% annual interest compounded monthly. And Bank 3 offers you 12% interest compounded continuously. And I want you to use mathematics to argue, make a formal argument. Why? Which one is the best? Which one is the second best? Which one is the third best? And why? So there should be numbers in your answer in terms of, well, actually I won't give it away, but your numbers, your argument should be quantitative in nature is what I will say, okay? So bit of an open-ended assignment here. I've given you the formulas. Go ahead and work with a partner to determine which one you think would be best based on your mathematical analysis. And I will walk around and help if anyone needs a little bit of help. Yes. So, Liv, can you go back and work with Ashley, please? Is there anybody else who doesn't have a partner? Lane, can you form a group of 3 with Mia and Ruth? Or Lane, maybe you can move over and work with Jenna, actually. Can you do that for me? Thanks. Kayla, can you work in a group of 3 with Carter and Jasmine? And then Alexandra, do you want to join up with Lily and Sully? Gavin, you got a partner? Working with Colin? Okay. Maybe you can get Andrew into your group as well, maybe. Good question. What is the principle? It doesn't say what the principle is, does it? What do we think about that? So we have one option, which is make it 1,000, right? Why don't I just make it 1,000, right? Or I could make it $1. That'd be even easier, right? See how much money I have after a certain amount of time, right? But what's important is the principle should be the same. I should imagine what is going to happen to my money if I invest the same amount of money in Bank 3, in Bank 2, and Bank 1. It doesn't matter what the amount is, because the rate of interest is what matters here, right? The rate at which I'm earning money depends on how much principal I have. So I just need to make sure that the principal is the same for each bank. So n should also enter into the number, right? N times t here, right? So n, right, is the number of times per year that we can count, right? So if we're doing annual, we count it annually, how many times per year do we count? Just one, right? So that's where we're gonna put one for n in both spots. Sorry? What was T, remember, represents how long the investment is for, right? So, in kind of similar fashion to the principal, right? So we want to make sure that if I want to compare the three banks, right? I want to take the same amount of money and invest it into each of the banks. Now, do I want to compare the amount of money I have in bank one after 1 year with the amount of money I have in bank two after 5 years? No, we want to make sure that the amount of time we make the investment is the same, right? So if I want to make a comparison of the interest rates, then I should hold everything else equal, right? So namely, the principal should be equal, and the amount of time the investment should be equal. Now, how much time do you want to invest? That's up to you. 10 years, 1,000 years, 1 year, something like that.
Or 2 years.
So this would be what you get if you invest in 12% annual, compounded annually for 1 year, because this would be 1 times 1 is 1, right? And then 6 here, yeah, let's do. Oh, wait, no, it's something wrong. So 1 times 1 plus 0.12 equals 1. Or we get when we divide 0.12 divided by 1. So this would be the same as 1 times 1.12. Okay, so you agree with me that if I divide something by 1, I haven't changed the number, right? So inside my parentheses, what do I have? 1 plus 0.12, so this can be rewritten as 1 times 1.12. And if I take anything to the first power, it's just itself, right? If I multiply a number by 1, what do I get? Just that number back. So this would be what you get if you invest $1 for 1 year in bank 1. So what I want to do if I want to see whether bank 2 or bank 3 is better, invest $1 for 1 year and see how it goes. All right, let's go into front.
I did.
Looks fantastic. Nice job. Oh, so it's
Yeah, it was. I was.
yeah.
Yeah, I don't know if I could do like finances or I get like, what do we put like? Let's see if I can make this help one. Yeah, like, I feel better about this next one than I did the first one. And she's So,
Okay, I am seeing a lot of groups are finished or close to finished, so we're gonna discuss this together. So, this is an example of something that you can come across in real life, right? In real life, I'm not gonna be there saying you invest $1,000,005 for 37 days. No, you need to think a little bit more abstractly than that. You need to think, well, okay, if I'm gonna choose between the 3 banks, what ultimately matters is the interest rate and the rate or the number of times which it is compounded per year, right? This is what matters. What should be, if we're trying to analyze just the interest rates, then we should hold everything else equal, right? Namely, I should invest the same amount of money in each bank. And if I want to compare Bank 1 and Bank 2, I shouldn't invest the money for 3 years in Bank 1 and for 5 years in Bank 2, right? I shouldn't do that. I should invest for the same amount of time. How much time? Doesn't matter. How much money? Doesn't matter. It just needs to be the same for each bank, right? So I need to invest a certain amount of money in each bank for the same amount of time for all of the banks, right? And then if I look at how much money I have after that amount of time, whichever one is growing faster, it doesn't matter if I am actually going to invest for 35 years or if I'm actually going to invest for 40 years. If I am earning more over a 1-year period or a 5-year period, I'm earning more over any other time period, right? So, it's up to you. You can choose your principal. I'm going to choose the easiest principal there is, which is $1. And I'm going to choose the easiest amount of time that there is, which is 1 year. I'm going to invest $1 for 1 year. So what do I get if I do that for the first one? I get 1 times 1 plus 0.12 over 1 to the 1 times 1, which if you do that, it's a lot of ones. We get 1.12, okay? Because this is what I get when I add 1 plus 0.12 over 1, I get 1.12. I take it to the first power, which means I get just itself, and I multiply it by 1, which means I get just itself. Okay, how about if I do Bank 2? I need to make sure that I do the exact same amount of money for the exact same amount of time. So I'm going to get 1 times 1 plus 0.12 over 12, because I'm doing 12 times per year. And then I do to the 12 times 1. So this is 1 times 1.01 to the power 12, right? 1.01 to the power 12, which is what? Did anyone do this? It's like 1.13? Okay, so something like 1.13, okay? So I have 1 more cent in Bank 2. How about Bank 3? Well, I'm going to do 1 times e to the, what should the power be when I do continuous interest rate? It should be the rate times the time. So what's the rate? The rate is 12%, so it's 0.12. And I multiply that with the number of years, which is 1. So I just get e to the 0.12, which is what? Does anybody have it? Get the calculator out. It goes sideways, man. Sorry? Okay, but it should be probably, we should compare down to more decimal places.
I think Bank 2 is 1.26 and Bank 3 is 1.2.
Yeah. So if I do, let's do 1.01 to the power 12. We're going to need more decimals to compare these. This is 1.1268225 ... Okay, so we can see that here we get just 1.212.0 like 000, right? 000 ... Yeah. It's a terminating decimal. Here we have something which is a bit larger than that, and here we have something which is a bit larger than that. So which bank is the best for investing? Bank 3. Which bank is the best for borrowing? Bank 1, right? When you're borrowing, you don't want interest, right? You want the lowest interest rate possible when you're borrowing money. Okay. So those are the 3 banks that we have. This is how we can compare them. You could do $1,000 for 10 years. You could do $1 million for half a year, whatever you want to do, okay? So, yeah. Any questions on this one? All right. Then let's discuss some of section 3.2. We'll get through what we can today. So we have sort of begun discussing these exponential functions. And one of the really interesting things about exponential functions is that if you look at them, at their graph, you're going to notice something, which is not only do they pass the vertical line test, they also pass the horizontal line test, right? If I were to draw a horizontal line anywhere on the graph of this thing, it would only touch the function at most 1 point, right? So if it passes the horizontal line test, then what kind of function is it? It is a one-to-one function. So why is it important for a function to be one-to-one? Why was that interesting? Does anyone remember? If it is one-to-one, it has an inverse. Very good. So that is what we're going to talk about now. So we have a mechanism by which we can exponentiate. We need to have a mechanism by which we can undo that, right? Same deal with like multiplication. I have a way of doing multiplication, right? How do I undo multiplication? I divide. How do I undo addition? I subtract. How do I undo exponentiation? I use a logarithm. Okay, so for all these processes, we have an undoing operation, right? We can do things and we can undo them. So that's what we're going to talk about now. So if f of x equals a to the x is it is a one-to-one function, okay, always. So it has an inverse function, f inverse of x. So we write it with the f negative 1. And we have a special name and a special notation for this inverse function, which is log a of x. So this is actually how the logarithm is defined, okay? This is not to say that, well, there is an inverse and it happens to be the log. No, we are defining the log to be the inverse of the exponential function. That is what a log is, okay? So what does that mean? Well, that means that if f of x equals y, then f inverse of x, which is just log a of y, this should be f inverse of y. Okay, what does it do? If you put the output in as the input in the inverse function, then you get back the original input which gave that output for our original function. That sounds like a tongue twister. Let's see what it looks like in reality. Well, if I have a function, so here I have a function f of x equals 2 to the x. Well, let's look at some different inputs. Well, if I do 1, then I get 2 to the 1, which is 2. If I do 2, then I get 2 to the 2, which is 4. If I do 3, I get 2 to the 3, which is 8. If I do negative 1, I get 1/2, right? So what should be true about the inverse function? Well, the f inverse function, which is the log function, log 2 of x, should do what? If I plug in an output of the original function, it should give me back the input. So if my input for the log function is 2, what should the output be? 1. If the input is 4, what should the output be? 2. So you can see that the outputs here are just the inputs of the log function are just the outputs of the exponential function, right? So we just reverse this whole table, 8, 3, and if I did log 2 of 1/2, I would get negative 1, right? That's another way of writing it. I plug in 1/2 into the log function, I get negative 1. So it tells me, basically, what power must I take the number 1/2 to, no, what number must I take, excuse me, what power must I take 2 to in order to achieve the number 1/2? This is how the logarithm works. Okay, so yeah, in other words, okay, we can write 2 equations for every exponential equation. We can write a corresponding logarithmic equation. And for every logarithmic equation, we can write a corresponding exponential equation. So for example, 2 to the 3 equals 8 can be rewritten using logarithms by saying that log 2 of 8 equals 3. So if I plug in 8 into the log 2 function, what I need to find is the number such that if I take 2 to that power, I get 8. Okay, so this is for most of my students, this is one of the more confusing subjects in pre-calculus. So my guess is many of you feel the same way. And the only way which you can cure confusion in math is practice, okay? So practice, 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 practice. I'll probably put some extra log practice on the blackboard for you to do if you want to get more familiar with this stuff. Okay, so this is basically logarithms. See a couple people still writing, so I'll wait for a second before we move on to some partner practice. All right, so remember, these are the functions which undo one another. All right, so let's try with a partner now. I'd like you to try converting. Okay, using this process, I want you to try converting one of the exponential equations into a log equation. And I want you to try converting a log equation into an exponential equation. Okay, so go ahead and take a couple minutes to try that with a partner. And then we'll discuss. Okay, does any group need a little more time to work? A little more time, okay. Take another 30 seconds or so. Okay, we ready? All right, so one thing that I feel helps with this is sometimes people like to memorize a certain phrase, okay? And it comes from the following. If you look at the exponential equation here, you can identify its parts in the following way. You can call this the base. You can call this the exponent. And you can call this the argument, or some people call it the answer. Does anybody have anything else that they call it? Maybe right-hand side or something like that. I don't know. Anyways, this is what you can call these you can label these parts of the exponential equation. And then you can remember how to convert it into a logarithmic equation if you remember the following phrase. Log, and I just read from left to right, log base argument equals exponent. Okay, so this will teach you how to convert from an exponential function, because I think it's not too hard when you look at the exponential function to know what is the base, what is the exponent, what is the argument, right? If you remember this phrase, then you exactly know, well, I know the 2 needs to go right here. I know the 3, that's the exponent, so it needs to go on the side where I write exponent. And I know that 8 is the argument, so it needs to go where I put the argument. So you can remember this simple phrase, log base argument equals exponent. If you remember that phrase, then you can know how to convert fairly easily. So that's one method some people use. So let's take a look at these two equations. Well, my base is 4, my exponent is 3, and my argument is 64. So what should it be in log base? So it should go log, what's the base? 4. What's the exponent? 3. So where does the exponent go? After the equal sign. How about 64? It's the argument, so it goes here. Okay, so log 4, 64 equals 3. Okay, so we're just rearranging these numbers, right? We're rearranging them. We're putting the exponent on one side, right? Okay, how do I do this one? I have, remember, log base argument equals exponent. So what is the base here? The base is 2, so I'm going to write 2 on its own. And what is the power which I'm going to take 2 to? It's the exponent, which in this case is x. And it's going to be equal to the argument, which in this case is 5. Okay, so that's all I have to do, right? I'm just converting to log form. I'm not, converting to exponential form. They don't ask us to solve for x. Sometimes they will ask us to solve for x, which is what we're going to talk about next. But are there any questions about converting between exponential form and log form? Okay. Well, I'm sorry to say I'm going to keep talking for quite a while longer because there's just a lot of things which I have to tell you, unfortunately, with this. But we're going to keep trucking. So this is how we convert between log and exponential form. It's very important to remember how we do it. I don't care how you do it, but this is one way that I find students have had success with, is to remember this kind of how you say this phrase, log base argument equals exponent. You write it down in left to right order, right? Okay. So let's talk about how we evaluate logs. Well, the log function is a function. If I plug in a number, then I should get a number as an output, right? This is what a log is. So when I say log 5 of 25, okay, I'm talking about the number which I get when I plug 25 into the log 5 function, okay? So if I want to know what is that number, then what I am searching for here is the number x, such that if I convert this into exponential form, what would I get? I would get a new equation. What should that new equation be? Yeah, 5 raised to the power x equals 25, okay? So the base is 5, the powers, or the exponent, sorry, the base is 5, oh my god. The base is 5, the argument is 25, and the exponent is x. So 5 to the x equals 25. What should x be? 2. That's the number, such that if I do 5 squared, I get 25. Okay, so how about the next one, log 1/3 of 9? It's not as easy to see what that one's going to be, but let's rewrite it. Well, the base is 1/3, right? What is the power? What should the power be? Yeah, just x, okay? I'm searching for the number x, which this is equal to. and it's to be found, right? So is equal to 9. What power must I take 1/3 to in order to get 9? -2, right? Because 1/3 to the -2 would be 1 over 1/3 squared, which if I divide by 1/3, that's the same as multiplying by 3. So this is 3 squared, which is 9. Okay, so in this case, x should be -2. That is the power which I should take 1/3 to in order to get 9. Are there any questions on how we can evaluate some logs using exponential functions? Let me ask a general question. Is there any limitation to using this method? Can you think of a circumstance where maybe this method wouldn't work so well? Yeah, Lauren? Well, negative numbers, right? I can't do the log of a negative number. Why can I not do the log of a negative number? Because that would mean that if I try to do like log 2 of -4, right? Well, if this is equal to x, then this means that 2 to the x equals -4. Why is that not possible? Well, 2 is a positive number, right? Take it to a positive power, or any power, you get a positive number. What does the graph of 2 to the x look like? It looks like this. It's never going to be equal to -4, is it? Right? So we can't do logs of negative numbers. But there was a more specific limitation on this, besides the fact that we can't plug in a negative number. When is this not going to work so well? Was there anything particularly convenient about these two equations? Yeah, it's like really easy to see what the power should be, right? What if I gave you log 5 of 26? Then what would you get? If this is x, then you know that 5 to the x equals 26. So what's x? Well, it's not so clear, is it? What power must I raise 5 to in order to get 26? Right? It's not clear what the power should be. In fact, it's so not clear that people back in the day used to use tables, these massive books of logarithms, which would compute logarithms to like certain decimal places. And you would just, if you wanted to know what log 5 of 26 was, you'd turn to the log 5 chapter and you'd scroll down until you see 26 and you say, aha, it's like something like 2.015 whatever, right? So we used to look through those log books actually when I was in like middle school or whatever. I don't know if they still do that, but they exist. So that's what the limitation to this is sometimes you can convert to exponential and you can just see what should the power be, right? Sometimes not so much. Okay, any questions on evaluating logs using this method? Okay, we'll talk about more methods for evaluating logarithms later. But first I want to tell you about some properties of the log function. Okay? Well, the properties of the log function basically come from the properties of the exponential function. So maybe I'll write down the corresponding properties of a to the x. Well, if f of x is a to the x, then what is f of 1? That's a to the 1, which would be just a, right? So if I were to make a corresponding equation using logarithms, if a is the output when I plug in 1 for this function, then 1 should be the output when I plug in a for log, right? So, my God. Panic. Okay, so a is the output for a to the 1 means that 1 is the output for log of a. Okay, how about log a of a to the x? Well, what does this mean? This means that if x is the input, right, if x is the input, then the output is a to the x. So for the log function, if a to the x is the input, then x should be the output. Okay, so log a of a to the x is x. So log, if the power matches with the base inside here, we just cancel this whole log system and we're left with just x. Okay? So next up we have log a of 1 is equal to 0. Why is log a of 1 equal to 0? Can someone explain it to me? Why should log a of 1 be 0? Andrew.
That would be a raised to the power of 0.
Yeah, log a of 1 is equal to 0 because the corresponding exponential equation is what? A to the 0 equals 1. That's why this has to be true, because this is true. And if we convert it into log form, it looks like what we have written on the left-hand side. Okay, how about this last one? Why should this be true? Why should a to the power log a of x give us back x? Sorry? Yeah, they are going to cancel, and it's because of a special property, namely, these two functions are inverses of each other, right? So if you remember back to the inverse chapter, what did I get when I did f of f inverse of x? What should I get when I do f of f inverse of x? Well, the f inverse function, it does something. And what does the f function? It undoes whatever we just did. So I should get x. If I take a number, I do something to it, and then I immediately undo that operation, I get back the number which I started with. Okay, so that's why this should be true. This is like I'm plugging in the function log a of x. I'm plugging it in for x in the function a to the x. I'm plugging it into the function a to the x. Okay, we still got 3 minutes left, so let's make sure we talk about the domain and range here. So these are the inverse properties, right? Remember, the way that we checked whether two functions were inverses or not was to plug them into one another and see if I get x. And that's true here. If I plug a to the x into the function log a of x, I get x. If I plug the function log a of x into the function a to the x, I get x. If I take two functions and when you plug one into the other and the other into the one, I get x for both, then that is the definition of what it means to be inverse functions. So that is why log a of x and a to the x are inverses. Well, it's not why, but it's a demonstration of that fact. Okay, so let's talk about the domain and range. Well, to talk about the domain and range of an inverse function, you just need to take the domain and range of the function itself. What is the domain and range of a to the x? The domain is what? What kinds of numbers can I plug into the function a to the x? All real numbers. How about the range? 0 to infinity, including 0? Should I have a bracket or a parentheses? Parentheses, why? Can someone explain why I don't include 0? Because a to the 0 is 1? Do we agree with that? Yeah, it's true that a to the 0 is 1, but that's not why 0 is not in the output. What you're looking for is a number x such that if I plug it in, I get 0, right? And that's never possible. There's no number, there's no power which I can take, which is going to make that 0. So hang on, y'all. I'm getting to the punchline here. Promise we're going to finish on time. So this is the domain and range of a to the x. So what should the domain and range of log ax be? The domain of an inverse function should be what? It should be the range of the original function. And how about the range? It should be the domain of the inverse function. Okay, so that's domain and range of logs. We'll pick this up next time. Yeah, we'll pick this up next time.